Hello and welcome to the fourth episode of my Tidy Tuesday summaries. In this video I will summarize an 1 hour long live screencast from David Robinson, where he analyzes the US wind turbine dataset from the Tidy Tuesday project in R. We will map the location of thousands of wind projects across the United States and visualize their capacity, year of installation and number of wind turbines. We will also look at the correlation of turbine height and rotor diameter with the energy produced. If you're interested in the topic or want to see how tidyverse functions are used for analysis, stay tuned. We can load the dataset with the read CSV function that needs an URL address to the raw data CSV file, or we use the ttload function from the Tidy Tuesday R package that only needs the release date of the data. The dataset includes 58,185 rows, each corresponding to one wind turbine. The 24 columns hold information on the exact location, longitude and latitude. When the variable starts with T, it refers to turbine information, like in which state it's located, what the manufacturer and model is, its energy capacity in kilowatts, hub height, rotor diameter and total height in meters, as well as the rotor swept area in square meters. When the column starts with a P, it refers to project information, like the name of the project, the year it became operational, the number of turbines included, and the project capacity in megawatts. As you can see, there are many missing values that are specified as either -9999 or missing. This can be dealt with directly when we load the data with read CSV by specifying the NA argument, or we can clean it up later with mutate and if-else functions. Let us start with counting the different project names and sort them in descending order. If we follow up directly with a mutate, we can calculate percentages with n divided by sum of n. Now we see that 1831 turbines, which account for 3.15% of all turbines of this dataset, are part of the unknown Tehachapi Wind Resource Area 1, one of over 1400 different project names of this dataset. In the description I linked to the website of the data source, where you also find an interactive map. This project contains multiple sub-projects with many hundreds of turbines in California, and I think when they weren't sure to which project they belonged, they simply labeled them unknown. This happens in a few other areas as well, but should not matter much for this analysis. Let us now count the wind turbine installations per state. We use the same count and mutate function as before and see that the 13,000 installations in Texas account for 22.7% of all US wind turbines, followed by California, Idaho, Oklahoma and Kansas with around 5% and more, strongly representing the Midwest and Western US. Basic mapping is quite easy with ggplot. On the x-axis we put longitude and on the y-axis the latitude values. We add geopoints, the coordinate map and the theme function to get rid of the axes, lines and ticks. By default, plotting includes all points of the dataset, which turns the US into a tiny cluster of points because there's one outlier in the far east. You probably noticed Alaska and Hawaii and maybe even Puerto Rico, but did you know that Guam is a territory of the United States? To improve upon the map, we filter out these 4 areas and add state borders. To not repeat this every time we plot the data, we can store it as US wind processed, with some more cleanup operations like if-else, where we can turn -9999 into NA and also turn negative turbine capacities into NA. Mutate if can be used more generally for all numeric columns where we want to turn -9999 into NA with the if-else function. If we want to visualize the biggest projects on the map, we can make use of the fct_lump function that keeps the top 6 projects with the most wind turbines and lumps the rest together as other. Now in ggplot we specify color equals project name in the aesthetics mapping function. The result is a map where the other projects in pink are plotted over the top 6 projects spelled out in the legend. You can see a glimpse of the blue dot representing the State Line wind project in the northwest. To flip this order and first plot all the other dots, we can make use of the arrange function, where we ask if the project name is not other, which will be false for other and true for the top 6 projects. And since arrange orders from low to high and false is coded as 0 and true as 1, all the other dots get plotted first. With group by, project name and state and summarize, where the end function is used to create a turbine count, we get the following results. Instead of plotting each turbine individually, it makes sense to group them together by project and keep the turbine number information. Then instead of 190 closely clustered dots for the 251 wind project in California, we would only have one big dot with average longitude and latitude location values. Before we do this, we have to check whether some project names are used in multiple states. If we follow up the code with count on project name again, we get 15 cases of projects that are found in 2 states. Grouping wind projects that are on state lines together would not be a problem, but if the same generic wind park name was used in Florida and California, then grouping these together with the average location would be a mistake. Out of these 15 project names, only 4 are on state borders. Broadview Energy between New Mexico and Texas is one. The wind turbines in Indiana and Oregon don't belong together because they don't share a state border. Neither do Illinois and Vermont or Michigan and Washington. Leaning Juniper in Oregon and Kansas are also not related. Neither is Lincoln Wind Energy in Nebraska and Wisconsin. But Min Dakota is a project between Minnesota and South Dakota. The third one is the Stateline Wind project with a few hundred wind turbines both in Oregon and Washington. And Tatanka is number 4 between North and South Dakota. Now we can create a wind projects dataset that groups turbines together for each project name and state, where we use the mean, long and latitude, extract the start year as the minimum year a turbine went operational, and also calculate the total capacity by summing up all the turbine capacities. Because we use NA remove equals true and sum turbine capacity, we get some projects with 0 capacity that should be filtered out. Now we can plot the 1400 projects on the map with circle size representing the number of turbines. With a distinct function on project name and year, we can see that in the wind process dataset some projects have multiple different start years, because they added many more turbines over the years. The San Gorgonio farm started its first turbines in 1984 and constantly added turbines throughout the 90s, in 2008 and from 2011 to 2016. We took care of this in the wind projects data frame by only selecting the minimum year per project. With geom histogram we can see that wind turbines went first operational in the 1980s and then massively increased in the early 2000s, peaking around 2010. On the map we keep size linked to turbines, but we can also set color to start year, which will color the circle in dark blue for old projects that you find mostly in California and bright blue for newer projects that can often be seen in the middle of the US. Before we look at project capacities, we can plot the different capacities per turbine. We can do this with geom histogram, either on a log scale to add some more details on the capacities below 1000 kilowatts, or on the normal scale, which gets a bit squished together due to one capacity being as high as 6000. Let us move on to the project capacities now. When we use the distinct function on the US wind process tibble and specify project name and project capacity and combine this with the count function, we gain information on whether a project contains different capacities. Here the McNeilus project contains installations of various NM models that are produced by the Danish company NEG Micon. Depending on the number of installations and the model type, we get a certain project capacity in megawatts. At this point, it does make sense to create a data set that combines the different capacities of the various installations of different models to a total project capacity. Now we can plot different total capacities of various projects over time. This gives us many points that often overlap, so it is advised to build an average that is easier to follow over time. When we group by start year and save the median capacity from all the total project capacities of this year and keep the number of projects this median is based on, we get the following result. In the 80s and 90s we rarely had more than a handful of projects created, with a median capacity of roughly 5,000 to 10,000. Then in the 2000s dozens of projects got built with median capacities ranging from 10 to 50,000 kilowatts. Visually we can summarize this with a line plot. Here we see the ever increasing median project capacity over time. If you want to know how many projects were started in the US over the last 4 decades and how many turbines they added, here's how you could do it. We use the wind projects dataset and put start year on the x-axis and turbines on the y-axis and add geom points and a geom smooth line. There were 3 projects that started in the mid-80s, but then it really picked up in the 2000s, with an average of 50 turbines per project, some even adding hundreds of turbines. When we divide the total capacity of the project by its turbine number, we can see how capacity increased over the years. Because we specified size in the aesthetics mapping function of ggplot, we get different circle sizes depending on the number of turbines per project. As you can see, after 2005, most new turbines had around 2000 kilowatt capacity, which then increased even more after 2010. We can put this information on a map with the brighter color representing projects with more total capacity and the circle size representing the number of turbines per project. Let us next investigate the different capacities of the wind turbines to see how much energy they produce. We have many thousand installations of various model types present, but how can we check if each model has a distinct capacity? With group by on the models and summarize and n distinct on turbine capacity, we see that the Vestas 110 has 4 different capacities and the GE 1.7 and 2.0 have both 3. With filter and select we can have a closer look. The group by and count adds the n, which can help us decide whether the capacity differences for the same model are errors or correct. The most common capacity for GE 1.7-103 is 1700 kilowatts, so the 1709 recorded only once might be a typo, but the 6 turbines with 1650 are probably real. Similarly, the V110-2.0 capacities are all backed by substantial numbers. We have to keep in mind that the Vestas comes at 2 different heights, 80 and 95 meters hub height or 135 and 150 meter total height. Even though the rotor is always the same, the capacity could be different for those. One way to resolve the capacity differences is to use the median for each model. And just to be safe, we can create a new data frame or table called turbine models, where we repeat this median selection not only for capacity but also for hub height, rotor diameter, rotor swept area and total height. And while we're at it, we can find the first year the model was used with the min function and add a count variable as turbines with the n function. The n distinct function can be used to find out in how many distinct projects this specific model was installed in. A lot of analysis can already be done with simply viewing this new data frame. We see that the GE 1.5-77 was installed 8,542 times in 147 projects, which is impressive given that half of the 255 different models were only used in 1 or 2 projects overall. We can sort this by first year to get a little history lesson on new models being created. When we sort by turbine capacity, we see the Haliade 150-6 is the clear king of energy creation, with 6,000 kilowatt and 5 turbines currently existing in the US, whereas other newer models have around 3,000 kilowatt. Now I noticed that the 3 digits in the model name refer to the rotor diameter, which is 150 for the Haliade 150 and 126 for the Vestas 126-3.45. The second number stands for the capacity. 6,000 kilowatts equals 6 megawatts, and the 3.45 from the Vestas in row 4 corresponds to 3.45 megawatts. In case you wondered how Haliade produces such an enormous amount of energy, those turbines are offshore installations, actually produced by the French company Alstom that was bought by General Electric's Renewable. Does the capacity correlate with the total height of wind turbine, or does only the rotor swept area matter, you may ask? ggplot and geopoint give the answer. As the wind turbine gets higher, it produces more energy, but there's quite a bit of variation. When you look at 150 meters, you get a range from 1800 to 3500 kilowatts. Correlation is a lot stronger for the RSA, especially in the beginning, but then also shows a lot of variation, where 2000 kilowatt can be produced by rotors sweeping 5000 to 10,000 square meters. At the end, I want to ask some quick questions to the dataset that weren't part of the original screencast from David Robinson. For example, I want to know how the 4 different turbine characteristics changed over time. To investigate this, we select the project year, the turbine hub height, rotor diameter and turbine total height, all in meters, as well as the rotor swept area in square meters. With NA omit, we focus only on turbines that have information for all of these values and exclude any row with a single NA. Before we can plot this in a more convenient way, we turn this white table with 5 columns and 51,000 rows into a long data frame with the pivot longer function. We don't want to gather the year, but the other 4 columns will be transformed in the following way. The names to argument turns THH, TRD and so on into the type, and the numeric values will be stored in a new size column as specified in the values to argument. We save this information in a new size time table. Here you can see the result side by side. We now have 204,000 rows because for each year the 4 characteristics repeat in the type column with the associated values stored in the size column. Now very often these values repeat, and instead of plotting over 200,000 points, which takes quite a few seconds and then very often just overlays many points on top of each other, there's a better way to do it. With count on year and measurement type and the size measurement, we can see that in 1981 the turbine hub height of 24 meters existed for 132 turbines. We can utilize this count information in ggplot by specifying size equals n. Now the dots represent how many values per size measurement exist. You notice the big smoosh for heights of roughly 80 meters that is very dominant from 2005 onwards. When you want to see the line below the points and also have the legend circles be better displayed, you have to change the order and first add geom smooth and then geom point. You remember that we produced the turbine models table where we created the first used column. Here I was interested in when a model first appeared on the market. The V47 appeared in 1982, was built by Vestas and produced 660 kilowatts. In row 241 you can see the Heliade 156 from GE first being used in 2016. Then I was also curious to see how different models of one manufacturers are installed over years. Here are filtered for General Electrics with the string detect function, where T model is the string and the pattern to be searched for is GE. Now we can plot all the different models that were used over the last 20 years. They had their flagship model, the GE 1.5-77, with more than 8,000 installations in total from 2005 to 2010, but then added a lot of different models afterwards. The same can be done for MWT, which represents Mitsubishi wind turbines that have fewer models on the market. Here the 4 single dots represents models that were only installed in a single year. The final thing I wanted to know is how many wind turbines were installed in the US over the last 40 years by different manufacturers. To not show all of them, we can mutate them with the FCT lump function, where we only keep the top 11 and group all the rest into another category. Now with group by on manufacturer and P year and count, we will get the number of turbines for each of the top 11 manufacturers for each year. NA omit gets rid of turbines that had no manufacturer or year associated with them. And then we can plot the line connecting the installations over time with separate plots for each manufacturer thanks to the FCT wrap function. We use scale equals 3y, again as the number differ quite a bit amongst manufacturers. You can see that General Electric's wins y-axis goes up to 3000, followed by Vestas having numbers as high as 1500 for a certain year, Siemens goes up to 1000 and others up to 600. Vestas being active already in the 1980s, GE and Siemens coming into the picture in the 21st century. This concludes the end of this video. I hope you learned something that you can use for your analysis and visualizations. The next video will be about malaria incidences, where we'll have a lot of mapping plots again. See you then, here at the Data Digest.